Richard James Mathematics Resources will now present Grade 4 Practice Paper 2, and we are taking a look at the problems that are contained in Section C. And Section C, like Sections A and B, will contain the solution of 12 problems. And the first two, one from 1 to 12, the other from 13 to 24. So we are at 25, and we will go all the way to problem number 36. The scores that 4 girls got in a game are shown below. The child with the highest score wins the game. Who won the game? So who won the game? I was told that it is Jane. Jerry is saying that it is Jane, because Jane got the largest or the highest score, so she won the game. The numbers are not far away still, but bring them closer for inspection. They are the numbers. They are not far away, but we will bring them closer for inspection. Now, by just looking, Jerry was able to tell that 32 is the highest number or the largest number. Therefore, the game would have been won by Jane. So actually, Jane won the game. So we are looking at the highest score. We may easily identify the largest number. It is the one with the largest digit in the largest place value column. The largest digit in the largest place value column. So which column is the one that is largest in place value, Jerry?
On the left.
The one that is to the left. So there we have the leftmost column is the one that is the largest place value. The largest place value is the leftmost digit. Which leftmost digit is the largest? Which leftmost digit is the largest? Of course, 3 is the largest. Therefore, the number that is the largest is 32,000. And that is the score. Who received that score, Jerry?
Jane.
Jane. And therefore, Jane would have won the game. The largest leftmost digit is 3, and it belongs to Jane. Jane has the highest score and therefore wins the game. The correct answer is option D. The diagram shows the shape of a garden, someone's garden. What is the distance around the garden? Distance around. What is the distance around known as in mathematics?
Perimeter.
Right, so Jerry knows that the distance around is perimeter. The most important phrase is distance around. This will tell us how far someone will travel if he walks around the garden. We need to add all of the distances that go around the garden. When we are through, we should have a closed circuit of the garden. That means we are going all the way. Say we start here. We go all the way around and we end there. Some candidates are able to tell that the 3-meter line is equal to the inside line. So we have this 3-meter line right here. And some candidates will be able to tell that this is the same. So it goes right there. Because of the line that is there, some candidates also erroneously include that line in the distance around. But it is not around, it is inside of the diagram and should not be included in the distance around. So we should not include this distance in the distance around, as some candidates might erroneously do. Distance around. As we mentioned before, we need to add all of the distances that go around the garden. When we are through, we should have a closed circuit of the garden. The distance around is called what?
Perimeter.
As such, we will designate to it the letter P. So the distance around is called the perimeter. And we will call the perimeter P. And I'm really impressed that Jerry gave the proper pronunciation of that word. So let us go around the garden. First we have 6 meters. Then what do we have? 5 meters. Then
10 meters.
10 meters. And finally
3 meters.
3 meters. And Jerry is also supplying the answer. He's saying that it is 24 meters. And he is correct. And that is represented by what option, Jerry?
B.
That is represented by option B. The word perimeter means the measurement around. The word perimeter means the measurement around. Other words with the root peri has to do with around. For example, pericarp, periscope, and periphery. Pericarp, periscope, and periphery. And pericarp is the outer coating of a seed or a nut. Periphery, we are talking about the region that surrounds something. So anything that has to do with the root peri has to do with something that is around, surrounding, or something that is all the way around. The calendar shows September 2006. What day of the week is September 25th, 2006?
Monday.
Jerry is saying it is Monday. The question is about September 2006, and the calendar is about September 2006. The information is directly related to the question. This is September 2006, and the question is about September 2006. What day of the week is September 25th, 2006? Jerry said that it is a Monday. What day? The answer that we are looking for should tell us the day. And no doubt, in the options we have days in a particular week. The 25th of September. So let us find the 25th. The number day in the calendar is 25. First, identify the 25th day of the month. There it is. Then identify the day of the week that it is associated with. It is associated with Monday. Therefore, the 25th of September 2006 was actually a Monday. The arrow points directly to Monday. This tells us that the 25th of September 2006 was a Monday. The correct answer is therefore option C. We have the same calendar, the same month of the calendar also, September 2006. What day of the week is the last day in August? Let's see if Jerry can figure that out. This is September. What day of the week is the last day in August?
Saturday. The last day in August.
Right.
Thursday.
It has to be a Thursday because September started on a Friday. So the last day of August has to be the day before the Friday on which September started. So what day? Again, we are looking for the day. The day that we are looking about, or the day that we are talking about, is the last day in the month of August. Last day in the month of August. And there we have the months of the year. January, February, March, April, May, June, July, August, September, October, November, December. We go from August to September. August is the month that comes just before September. The last day of August is the day that comes just before the first day of September. The last day of August is the day that comes just before the first day of September, which is that day. We don't have to look very far for the day. It is a Thursday. The day of the week is Thursday, and it is option B. So the last day of August is that day that comes just before the first day of September. What is the most appropriate unit to measure the amount of soda in a small bottle? That's a very good question. What is the most appropriate unit to measure the amount of soda in a small bottle? Amount. The amount of soda may be its mass or its volume. Its volume is the amount of space occupied. For example, the amount of space taken up in a container. The amount we are talking about may be gram or maybe milliliter. We are taking a look at those two options, and we will see why we are considering them, because we are sure that the correct answer is, which one do you think is the correct answer?
Option C, milliliter.
So Jerry is saying that option C is correct, and I think he is correct, but let us see why he is correct and how the other options are incorrect. If the amount that we are talking about is mass, then gram is applicable. But if the amount that we are talking about is the amount of space occupied, the amount of space it occupies in a bottle, then milliliter is appropriate. So we have most appropriate and we have small bottle. So we are paying attention to that phrase or those phrases. 1, most appropriate, and the other one, small bottle. The examiner is by no means assuming that only one answer will work. That is why we need to pay attention to the operative term, most appropriate. The term also, which is in a small bottle. This one, the term in a small bottle, eliminates the unit of mass, which is gram. So in a small bottle, that gives the impression of the space that is occupied in the small bottle, and therefore we will not consider any unit that has to do with mass, like gram, kilogram, or so on. So milliliter will be the correct option. The correct answer is milliliter, and that is option C. So we may think of amount as being mass or the space occupied, but we have to take a look at the operative term, most appropriate, and also that we are talking about soda in a small bottle. And if we are talking about soda in a small bottle, then the space occupied by the soda is going to be the most important thing. And when we are talking about the space that is occupied, we are talking about the volume. And the volume, the unit of volume that is present in the options is milliliter. Now we are taking a look at our system. The metric system may contain tables, as we have for this one, is units of length. So 10 millimeters equal 1 centimeter, or sometimes we don't say equal. We say 10 millimeters, 1 centimeter. 10 centimeter, 1 decimeter. 10 decimeter, 1 meter. 10 meter, 1 decameter. 10 decameter, 1 hectometer. 10 hectometers, 1 kilometer. Right. And we hardly sound the plural here, the plurals that we have there. We generally do not sound them when we are saying the tables. So that is what we have. These are the units of length or distance. It means that a length may be given in those units. However, because of the size of each unit and the likely length or distance, one unit may be more suitable than the other. For example, if I'm measuring a line in my exercise book, then I would prefer to measure that line in centimeter or maybe millimeter. If I'm measuring the distance from my building to the building across the street, I might want to measure that in meters. And if we are talking about athletics and the distance for each race, we may measure that also in meters. But when we talk about distances from city to city and community to community, then kilometer is going to be most appropriate. Two of the popular units of length in our daily lives are centimeter and millimeter that we have on rulers and other instruments in our geometry sets. Those units are suitable for the diagrams that we draw in class or in an examination. The grid on our graph paper is also given in terms of them. So we have the very tiny squares, those are 2 millimeters, and we have the medium-sized square, that's a centimeter square, and then we have the larger square, and that will be our 2 centimeters square. So the grid on the graph is also given in millimeters and centimeters. And there is a typical ruler that we use in our geometry set. That ruler has divisions that are given in millimeters and also centimeters. The other most popular units of length are meter and kilometer. Meter is popular in the distances that we have in track and field. So I'm asking Jerry, what is Usain Bolt's favorite distance on the track?
100 meters.
I did not hear. That is not loud enough, Jerry.
100 meters.
Okay, that's 100 meters. Well, as a matter of fact, the 100 meters is the race that makes him very popular. But the one that Bolt himself says is his favorite distance is what?
200 meters.
Right, 200 meters. And do you know, Jerry, that Bolt also used to run the 400 meters? As a matter of fact, yes, do you know that?
Yes.
And do you know that he did not used to run the 100? Okay, did not used to run the 100. Right. And he used to run the 400 meters. As a matter of fact, I saw him training at his school in 400 meters quite a few years ago when I was teaching mathematics to some teachers at his school, which is William Knibb Memorial High School. And they have a nice color. Their colors are, I think, purple, green, and blue. I'm not so sure, but I'm sure that purple and green in that combination. Right. Now, here we have a few calculations that you need to be mindful of, Jerry. So I hope that you are paying attention. It is plain from the table that 10 millimeters is equal to 1 centimeter. But if we go from centimeter and we go down, how many millimeters are 1 decameter? If we move the right side to the very next line, we need to include an additional 0. So 100 millimeters is equal to 1 decimeter. And if we move down the right side of the table, we have what? We go again, we include another 0. So if we move down the right side again to the subsequent line, we include another 0. So 1000 millimeter is equal to 1 meter. And if we continue to move down, then what will we get? 10,000 millimeters will be equal to 1 decameter. So if we keep going down, we multiply by 10 each time, as long as the one over here is kept still. So 10 millimeters, 1 centimeter. 100 millimeters, 1 decimeter. 1000 millimeters, 1 meter. 10,000 millimeter, 1 decameter, and so on. The rule may be generally applied to the table and it does not matter which row of the table that we are beginning with. On this occasion, we will begin with centimeter. So we will begin with centimeter. 10 centimeters, 1 decimeter. And if we move this one down, we will have 100 centimeter is equal to 1 meter. And if we move further down, we have what? 1,000 centimeters equal to 1 decameter. And if we continue down, we have what? For our hectometer, we have 10,000. So we will begin with 10, then we have 100, then we have 1,000, then we have 10,000. The sequence continues, and an additional line means another trailing zero on the left. So every time we go down one line, we include another trailing zero, which means that we are multiplying by 10 each time. There we have our table again. Notice that all of these units have their prefixes and they are in relation to meter. Let us take a look at what they mean. Milli means what? 1 part out of a 1,000. The prefix milli means 1,000th of. A millimeter is 1,000th of a meter. When you divide a meter in 1,000 equal parts, 1 part is a millimeter. Centi. Centi means out of 100 or 100th of. A centimeter is 100th of a meter. Deci. Deci means 1/10 of. A decimeter is 1/10 of a meter. And do you know deci? Anything else? Decimal. And decimal has to do with your base 10. Our regular number system has 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Deca equals 10. Deca means 10 times. A decameter is 10 meters. Hecto. Hecto means 100 times. A hectometer is 100 meters. Kilo is your favorite. 1,000. Kilo means 1,000 times. 1 kilometer is 1,000 meters. And notice that they always write the year 2000 as what? Y2K. Y2K. So the 2K means 2 kilo, which means 2,000. So the year 2K means the year 2000. It is easy to transfer back and forth in units when we are dealing in the metric system. 100 millimeter is equal to 1 decimeter. Therefore, 1/100th of a decimeter is equal to 1 millimeter. So if we are going in one direction, to go in the opposite direction, we do the opposite thing. So if we multiply by 10 to go in one direction, to go in the opposite direction, what do? We divide by 10. So we have 10,000 millimeters is equal to 1 decameter. So if we have 1 decameter, to get 1 millimeter, we will have to divide that by 10,000. 100 centimeters equal 1 meter. If we have 1 meter and we want 1 centimeter, we will have to divide that by 100. Volume, which is the amount of three-dimensional space. So volume, which is the amount of three-dimensional space. And that is measured in liters. The prefixes and their multiples are applicable for liters as they are applicable for meters. So we'll have the same. The most popular units in our table that are used are milliliter and liter. The large plastic bottle of Pepsi is approximately 2 liters. Apart from the large jugs of cooking oil, of the other two sizes, the larger one is usually a liter, or approximately a liter. So the big jug, that's not a liter. That may be 4 liters or 2 liters or maybe 3 liters. But the two smaller sizes, the larger one is usually a liter. So in our regular dealings, we have liters and milliliter. So the large bottle of Pepsi is a 2-liter bottle, and then we have your medium-sized bottle of cooking oil, maybe a liter. And what about the milliliter? Any size that is given below a liter is usually quoted in milliliters. Generally, if the capacity of a bottle is less than a liter, then its capacity is given in milliliter. The smallest bottles of cooking oil are usually approximately 500 milliliter. What about your units of mass? The table is the same. The prefixes are the same. The multiples are the same. The most popular units of mass are milligram, gram, and kilogram. Milligram is popular for the amount of active ingredients in medications. For dietary amounts or the nutrients in foods that you will find on labels of food packages, etc., they are usually given in grams and milligrams. So dietary amounts and the nutrients in foods, they are generally given in grams and milligrams. And we have there the most popular units are milligram, gram, and kilogram. That is for the measurement of mass. And the active ingredients in medications are usually quoted in milligrams. The mass of humans and also the overall mass of daily food items are usually given in kilogram. So Jerry, your mass, what is your mass given in, Jerry?
Kilograms.
Okay. So if you say milligram, it means that you would be maybe just the size of a louse or something like that. And of course, we have thousands of kilograms, and that will be what? 1 ton. 1,000 kilograms is equal to 1 ton. And the ton is usually used in reference to motor vehicle and also livestock like cattle, and so on. The mass of motor vehicles and large livestock like cattle and pigs are also given in tons. But if you take a look at the weight that is given on your driver's license, you will realize that it is given in kilogram. But outside of that, we have the mass of motor vehicle also given in tons. What temperature is 8 degrees cooler than 30 degrees Celsius? What temperature is 8 degrees cooler than 30 degrees Celsius? What do we mean by cooler than? On the thermometer, the larger numbers represent warmer temperatures. The smaller numbers represent cooler temperatures. So we have the hotter temperatures at the top and the cooler temperatures closer to the bulb of the thermometer. 8 degrees cooler means 8 degrees less. So if you are going cooler, the temperature is going down. The number representing the cooler temperature must be less than 30. We will subtract 8 from 30. So if we have a particular temperature and the temperature somewhere else is cooler, it means that the number representing the temperature, as long as we are talking about the same scale, will be a smaller number. The smaller temperatures are represented by the smaller numbers. So if we are talking about 8 degrees cooler than 30, it means that it is lower than 30 degrees by 8 degrees. So 8 degrees cooler means that if we are at 30, we will be going down in temperature and we will be going lower and lower in the number that represents the temperature. We cannot take 8 from 30, so we go to the greater place value and rename the 3. And the greater place value is always what? 10 times the present place value. And the greater place value is located to the
left.
To the left, as said Jerry. So rename the 3 to 2. So we are taking out 1 unit there. But the place value to the left is always 10 times the present place value. So when we put it right there, we will put it there as 10. 1, 0. So 10 minus 8 is equal to 2. And there's nothing to be taken away from the other 2. It returns just as it is. The correct answer is therefore option C.
B.
Oh, Jerry is correcting me. As I said C, Jerry said
B.
right. So the correct answer is option B. 22 degrees Celsius. 22 degrees Celsius. That is represented by option B. So I hope that I don't shade C. So represented by option B. 8 degrees cooler. We could magnify the scale of the thermometer and use it as follows. So magnify the scale of the thermometer and use it. Magnify the scale of the thermometer and use it. That is what we will do. Magnify the scale of the thermometer. Let's go. Well, we have it right over there. 8 degrees cooler than 30. Go to the 30 degrees marker. Where do we have 30 degrees? Right there. So we go to 30 degrees. So we have 30 degrees right there. We need to go cooler by 8 degrees. This means that we need to decrease the temperature by 8 degrees. Using our pointer, let us step by 8 degrees, getting cooler each time. The number representing the temperature will get less. So for a cooler temperature, we will have a smaller number, and we are going cooler by 8 degrees. Therefore, we will step down 8 degrees. Let's go again. 1, 2, 3, 4, 5, 6, 7, 8 degrees. Again, we end at 22 degrees Celsius. This confirms our answer as option
B.
Okay. So we are at 30 degrees Celsius, and we need to get cooler by 8 degrees. We need to decrease the number representing the temperature. Therefore, we need to go down each time. The number should be getting less. While this method is valid for all similar cases, it might not be time efficient in an examination. However, it may be used for practical demonstration. So this method, it might not be time efficient to draw a section of the thermometer and then step through it like that. In an examination, we might just say 30 minus 8. But for a practical explanation and demonstration, then this is a very good method to use. Before we solve this problem, there are two things that we need to look at. After we solve it, we will take a look at many others. So we are about to solve a problem, and we are taking a look at a few things before we solve the problem. The first one is perpendicular. What do we mean by perpendicular? What do we mean when we say perpendicular? If two lines are perpendicular, then the angle between them is a right angle, which is equal to 90 degrees. So perpendicular means that the lines are at right angles to each other, and the angle representing that right angle is 90 degrees. Such right angles that are 90 degrees and represent sides that are perpendicular, we may find in a rectangle. So the right angles that are 90 degrees and represent sides that are perpendicular, we may find those angles in a rectangle. So there's your rectangle, and we have 4 angles, each measuring 90 degrees. And a 90 degrees angle is the only angle that is correctly demonstrated by making use of straight lines. All other angles are represented by a curved line. When walls are perpendicular to each other, like in a house, colloquially we say that they are square onto each other. We say lengths, distances, lines or directions are square. When we say that, we mean that they are perpendicular. So when lines are square on, we mean that they are perpendicular. And if they say, take a look at that, that looks square to you? It means, does that look perpendicular to you? That's what it means. When lines are parallel, the perpendicular distance between them is the same throughout their lengths. So if we measure the perpendicular distance between lines that are parallel, everywhere we will find that the distance will be the same. When lines are parallel, the perpendicular distance between them is the same throughout their lengths. There we have two lines. We will show that they are parallel by introducing a line that is perpendicular to them both. So those lines are parallel. If they are parallel, then the perpendicular distance between them is the same throughout. If you put this perpendicular line all the way down, it will fit exactly between the two of them like that, all the way throughout the length, because this line is perpendicular to these two lines, and these two lines are parallel. It means that if we go all the way down like that, it will fit exactly between the lines like that. By running a segment of the perpendicular along the length of the line, we may show that the perpendicular distance between them does not change. So the perpendicular distance between the two lines does not change. It means that the two lines are parallel, because the perpendicular distance between them does not change. Mathematicians generally say that if two lines are parallel, no matter how far you travel along them, they will never meet. So parallel lines will never meet. And some mathematicians say that parallel lines meet at infinity. That means, since infinity does not exist, and it is such a distance away that if you keep going on and on, you will not get there, it means that the lines will practically never meet, no matter how far you travel along them. Mathematicians generally say that if two lines are parallel, no matter how far you travel along them, they will never meet, which is correct. What is the name of this shape? That is problem number 31. What is the name of this shape?
A rectangle.
And Jerry is saying that that shape is a rectangle. The shape has four sides. It is a quadrilateral. Right. A rectangle is a quadrilateral. So it is a quadrilateral. So it is not a circle and it is not a triangle. The only quadrilaterals that we have there are square and rectangle. Circle and triangle are incorrect. Outline all of the special features of the shape. So the shape that we have there, we will outline all of the special features of that shape. All of the angles are right angles. All of the angles are right angles. Not some, all are right angles. So notice that we have this line going like that. It means that those two lines are parallel. Those two lines are parallel also because it goes across and it is the same distance all the time. So those two lines are parallel and the other two are parallel. Opposite sides are equal in length and they are parallel. Opposite sides are equal in length and they are parallel. Let us take a look at all of them. The shape has how many sides?
4.
It is called a?
Quadrilateral.
It is called a quadrilateral. All 4 angles are right angles. Opposite sides are equal in length. Opposite sides are parallel. We don't have to mention all of them. If a quadrilateral has 4 right angles, then opposite sides are equal and opposite sides are parallel. Opposite sides of a quadrilateral are equal if and only if they are parallel. What do we mean if and only if? It means an if that goes in both directions. So let us show you what that means. Opposite sides of a quadrilateral are equal if they are parallel. Opposite sides of a quadrilateral are parallel if they are equal. So if and only if is an if that works in 2 directions. So for this shape that we have there, it has 4 sides. All 4 angles are right angles. Opposite sides are equal in length and opposite sides are parallel. What about the square? A square has all of the features of a rectangle. As a matter of fact, it is a rectangle. Did you know that, Jerry?
Yes.
A square is a rectangle and it has all of the features of a rectangle. All squares are rectangles, but not all rectangles are squares. Which rectangles are not squares? The rectangle in which not all sides are equal, those rectangles are not squares. For the figure to be a square, not only all angles but all sides must be equal. So a rectangle is not necessarily a square, but a square has all of the features of a rectangle. Additionally, all of the sides of a square are equal, but all of the sides of a rectangle are not necessarily equal. So those rectangles are not squares. For the figure to be a square, not only all angles but all sides must be equal. If all angles of a quadrilateral are equal, each must be a right angle. Why? If all angles of a quadrilateral are equal, each must be a right angle. This is true with all rectangles, but the square is the only one with all sides and all angles equal. In the shape, opposite sides are equal, but not all sides are equal. So in this shape that we have here, the opposite sides are equal, but all of the sides are not equal because this side is not equal to this one. So in the shape that we have there, opposite sides are equal, but not all sides are equal. The shape is therefore a rectangle, and option B is correct. It is a rectangle. A polygon is any two-dimensional shape that is formed only with straight lines. So a polygon is any two-dimensional shape that is formed only with what kind of a line, Jerry? Only straight.
Dimensional.
And it must be two-dimensional.
Two straight lines.
All lines must be straight. So there we have them. all of those are polygons. All of those that we have there are polygons. They are polygons, every single one, because each one of them is formed by straight lines only. So irrespective of the shape that we have there, each one is a polygon because it is formed by making use of only straight line segments. A regular polygon is one which is equiangular. That means all angles are equal, and it must be also equilateral. All sides are equal. So if we have a regular polygon, all of its sides must be equal, and all of its angles must be equal. So there we have our favorite, the equilateral triangle. And for the equilateral triangle, all of the sides are equal and all of the angles are equal. An equilateral triangle is regular because as long as a triangle is equilateral, it is also equiangular. Right. That means all angles are equal. Equiangular means equal angles. All angles are equal. So for an equilateral triangle, all of the sides are equal. That is why it is called equilateral. But it is also equiangular. All angles are equal. Square, that is your square. The regular quadrilateral is a square. The interior angles of a square have a sum of 360 degrees. All angles in a square, when we add them, or any quadrilateral for that matter, the angles will add to give 360 degrees. All angles are equal. So because all angles are equal, we need to divide 360 by 4, and the result is 90. 360 divided by 4, and the result is 90. That is why each interior angle of a square is equal to 90 degrees, because they are all equal and they have a sum of 360 degrees. When you divide 360 degrees by 4, the result is 90. We may say that they are all right angles. So those 90 degrees angles of a square, they are all right angles. A rectangle is a quadrilateral with all interior angles equal. Each of them is therefore equal to 90 degrees. That is your rectangle. A square also fits that description. It is therefore a rectangle. It has 4 sides with all angles equal to 90 degrees. However, for a rectangle, it is not necessary for all sides to be equal. As a consequence of having 4 equal angles of 90 degrees, opposite sides of a rectangle are equal. So we mark those with 2 dashes, meaning that they are equal. And of course the other will be marked with 1 dash. So these two are equal. So opposite sides of a rectangle are equal, and notice that the opposite sides are marked with the same number of dashes. Opposite sides marked with the same number of dashes. This has 1 dash, this has 1 dash, meaning that they are equal. This has 2 dashes, this has 2 dashes, meaning that they are equal. And the same applies there. Because a square is a rectangle, opposite sides of a square are also equal. Therefore, in a rectangle, all interior angles are equal to 90 degrees, which causes opposite sides to be equal. However, a square has the additional property that all sides are equal. So notice that a square, when it is drawn and it has dashes on the lines, all of the lines will have the same number of dashes, meaning that all of the sides are equal. Therefore, a square is a rectangle, but a rectangle is not necessarily a square. We will see other categories of quadrilateral that a square and a rectangle fall into. So other categories of quadrilateral. That quadrilateral is a parallelogram. Any quadrilateral in which opposite sides are parallel is a parallelogram. Because opposite sides are parallel, opposite sides are also equal. Opposite sides of a parallelogram are equal. A parallelogram has opposite sides that are parallel. And because opposite sides are parallel, opposite sides are also equal. In a parallelogram, it is not necessary for all of the angles to be equal as in a rectangle. However, as a consequence of having equal opposite sides, opposite angles are also equal. So opposite angles of a parallelogram are also equal. So those angles, the green ones, are equal, and those, the purple or lavender, they are also equal. In order to be a parallelogram, it is only necessary for opposite sides to be parallel, and therefore equal. Squares and other rectangles all fit this description. It therefore means that squares and other rectangles are also parallelograms. So square is a rectangle, it is also a parallelogram. And all rectangles are parallelograms. We have the rectangle and we have the square. And now we are demonstrating the sides that are equal. Any quadrilateral in which all sides are equal is a rhombus. What is a quadrilateral called when all sides are equal, Jerry?
A rhombus.
It is called a rhombus. A rhombus is a quadrilateral with all sides equal. Each side has a single dash. Because all sides are equal, it means that opposite sides must be equal. Because all sides are equal, so opposite sides must be equal. This means that a rhombus is also a parallelogram. This makes a rhombus a parallelogram. As a consequence of having equal opposite sides, opposite angles are also equal. So a rhombus is also a parallelogram. Opposite sides are equal, opposite angles are equal. In order to be a rhombus, it is only necessary for all sides of the quadrilateral to be equal. All sides of a square are equal. This makes a square also a rhombus. A rhombus has all sides equal. A square has all sides equal. Therefore, a square is a rhombus. All of the sides of the square are equal. Therefore, a square is a rhombus. Squares are rhombuses, but not all rhombuses are squares. Squares, rhombuses, and rectangles are all parallelograms. We will take a look at a property of all parallelograms. We have established that opposite angles of a parallelogram are equal. But what do we say about adjacent angles, which are angles that are beside each other? When angles are facing, adjacent to, when the angles are facing on the other side of, all the way over there, we say that those angles are opposite. When they are beside each other, we say that they are adjacent. Adjacent angles are formed by the same straight line. So these are adjacent. And if we do this, because this angle is on this line and this angle is also formed by the same line, then we know that those angles are adjacent. Adjacent angles have a sum of 180 degrees. Adjacent angles have a sum of 180 degrees. Notice that A and B are adjacent. When we add them, the result is 180 degrees. B and C have a sum of 180 degrees. They are adjacent, so their sum is 180 degrees. C and D are adjacent also. They have a sum of 180 degrees. And finally, D and A are adjacent. They also have a sum of 180 degrees. Rectangles are quadrilaterals, but is it true that adjacent angles of a rectangle have a sum of 180 degrees?
Yes.
Right. Because, first of all, a rectangle falls in the category of parallelogram. And for a parallelogram, adjacent angles have a sum of 180 degrees. Therefore, in a square, the adjacent angles must also have a sum of 180 degrees. All angles of a rectangle are equal to 90 degrees. This means that any two angles we add, they will have a sum of 180 degrees. So all of the angles are 90 degrees. So if we add any two, the result will be 180 degrees. It therefore follows that the sum of the adjacent angles of a rectangle are equal to 180 degrees. This is also true for squares, and other rhombuses. So if we add, as a matter of fact, in a square, the same is true for the angular arrangements. So it follows directly as the rectangle. And a rhombus is also a parallelogram. Therefore, the same is true for rhombuses. Any quadrilateral with two sides that are parallel is a trapezium, as long as the quadrilateral has two parallel sides. It is a trapezium. And there we have trapezia. And in America they talk about trapezoid. So we have there trapezia, which is the plural of trapezium. In geometry, parallel sides are shown by using arrows that go in the same direction. So we can mark the parallel sides of each one of those figures because we can place arrows that go in the same direction. So those are the two parallel sides of the yellow one. For the green one, we have the two parallel sides shown right there of the green one. And for the blue, we also have the two parallel sides. As long as the figure has how many parallel sides?
2.
And it has how many sides in all?
4.
So it has to be a quadrilateral. That means it has to have 4 sides. And it has two parallel sides. That makes it a trapezium. For a shape to be a trapezium, it is only necessary to have one pair of parallel sides. But if it has another pair of parallel sides, it is still a trapezium. So, if it has two pairs of parallel sides, it is a trapezium. But for it to be a trapezium, it is only necessary to have one pair of parallel sides. Squares, rhombuses, parallelograms, rectangles all fit the description of a trapezium. If two angles that share any of the parallel sides of a trapezium are equal, then the trapezium is called an isosceles trapezium. What we mean, this is one of the parallel sides and this is the other. If we have two angles that share this side and the two angles are equal, then the trapezium is isosceles. And this is another of the parallel sides. And we have two angles that share these parallel sides and they are equal. Then that makes the trapezium an isosceles trapezium. And if the upper two are equal, then the lower two will also be equal. The upper and the lower sides are parallel as indicated by the arrows. The green angles belong to the upper parallel sides and are equal. This makes the trapezium isosceles. And this also causes the two purple angles that belong to the lower parallel side to also be equal. So if these two are equal, it makes these two equal. And as long as any two of them are equal, two angles sharing any of the parallel sides, then the trapezium is called an isosceles trapezium. As long as the green angles are equal, then the pink angles which share the lower parallel sides will automatically be equal. So in an isosceles trapezium, the angles that share any of the parallel sides will always be equal. And if these two are equal, it follows that the other two angles that share the other parallel sides must also be equal. Two angles that share the same side of a polygon are called adjacent angles. This means that the two pink angles are adjacent and the two green angles are adjacent in the trapezium that we have there. So, two angles are said to be adjacent if they share the same line. Any quadrilateral in which adjacent sides are equal is called a kite. What do we mean by adjacent sides? Adjacent sides of a quadrilateral or any polygon for that matter are sides that share the same vertex or sides that meet. So these two sides are adjacent, these two sides are adjacent, these two sides are adjacent, and these two sides are adjacent. Any quadrilateral in which adjacent sides are equal is called a kite. Notice that we have here, Jerry, these two sides marked with 2 dashes and these two sides marked with 1 dash. Therefore, these two sides are equal and these two sides are equal. So these two sides are adjacent because they meet right here, and these two sides are adjacent because they meet right here. These two sides are adjacent sides that are equal, and these two sides are adjacent sides that are equal. Whenever we have a quadrilateral that is like that, then the quadrilateral is called a kite. Adjacent sides are sides that meet at a vertex of a polygon. In the diagram, equal sides are marked with equal number of strokes. The two upper sides are adjacent to each other and are equal and are marked with the same number of strokes. The two lower sides are adjacent to each other and are equal and are also marked with the same number of strokes. Because of the particular design of a kite, its diagonals meet at right angles. Its diagonal meet at right angles. A diagonal of a polygon is a line that joins vertices that do not share the same side. A diagonal of a polygon is a line that join vertices that do not share the same side. So if we want a diagonal, we have what? This vertex has these two lines, and this vertex has these two lines. Any case that we check right here, in any event, this vertex does not share any of the sides that this vertex share, because this one is sharing these two sides and this one is sharing these two sides. So this vertex has nothing to do with these two sides, and this vertex has nothing to do with these two sides. Therefore, the line that goes from this vertex to this vertex is called a diagonal. Rhombuses and squares are also kites. Rhombuses and squares also belong to the family of kites. They have pairs of adjacent sides that are equal, and as a consequence, their diagonals are also perpendicular. So in a kite, adjacent sides are equal. So if all sides of a quadrilateral are equal, then it is a kite. Because if all sides are equal, it means that adjacent sides must be equal. So squares and rhombuses are also kites. Which of these indicates a line segment? Which one of these indicates a line segment? A line segment. The diagram of a straight line has arrows at each end directed from each other. That's a line. Arrows at each end directed away from each other. Arrows at each end directed away from each other. That is the diagram of a straight line. It means that the straight line continues forever in those directions. The arrows show that it moves indefinitely in both directions, as in option B. So in option B, we have the diagram of a straight line. A line segment is a portion that is cut off from a line. A line segment has endpoints between which the segment lies. So the segment is a portion of a line, and it has endpoints. Sometimes the endpoints are not shown, but a line is a collection of points, and any segment of a line must therefore have endpoints. So there is your line segment, a portion cut off or segmented from a straight line. That's your line segment. Option D is correct. Options A and C represent rays. Options A and C represent rays. What is a ray? A ray emerges from a single point. The ray is directed away from that fixed point. That's a ray. It begins at one point and is directed away from that point. That is a ray, beginning at one point and is directed away from that point. The arrow that we have there shows that the ray will continue forever in that direction. That's a ray. The diagram of a ray contains a single point, which is the beginning, and a single arrow that shows the direction. So the single point and the arrow. The single point shows the beginning of the ray, and the arrow shows the direction in which the ray is going. We will continue with problem number 33. How many angles are in this shape? What shape? In a geometric shape, an angle is located at a vertex. Pluralizing the foregoing statement, we may say that angles are located at vertices. An angle is located at a vertex. Angles are located at vertices. So there is your shape. Angles are located at vertices. A vertex is a point where two line segments meet. We may say that a vertex is a corner point. So let us label the vertices. Label the vertices. A vertex is a corner point, or a vertex is a point where two line segments meet. So there are your vertices. How many angles are there in this shape? Although we can already see that there are 4 of them and option C is therefore correct, let us still go ahead and count them. So we know that how many vertices do we have there?
4.
We have 4. And we have them labeled A, B, C, and D. So put those numbers in. We have how many vertices? 4 vertices. Option C is correct. The angles are located at the vertices, but a vertex is not an angle. An angle is the amount of turn, which is a measure of the difference between the directions of the two line segments that meet at the vertex. An angle is a measure of turn. It is the amount of turn which is a measure of the difference between the directions of the two line segments that meet at the vertex, and we will take a look at what that means in a moment. Let us say that a vertex is located at the point A. Where is that? Oh, right there. A vertex is located at the point A. We have one of the line segments that form the vertex. So there is one. One of the line segments that form the vertex. In order to get the position of the other line segment that forms the vertex, we have to go through some degree of turning, like a door on its hinge, as if the hinge is located at the vertex. So let us repeat that. In order to get to the position of the other line segment that forms the vertex, we have to go through some degree of turning, like a door on its hinge, as if the hinge is located at the vertex. So we turn like that. There we have the angle, and it is indicated by using a curved line, as we have it right there. So we have our degree of turning, which will be the angle that is formed by those two line segments. And we have this curved line used to show the difference in direction between this line segment and this line segment. The arrows indicate that the turning is responsible for the angle. In getting from the direction of one line segment to the other, the greater the turning that has to take place, the greater the angle will be. So we have these arrows. Sometimes the curved line that is used is not accompanied by any arrow, but if the arrows are there, or whether or not they are there, it is our understanding that there is some amount of turning that causes the difference in direction between this line segment and the other. The arrows indicate that turning is responsible for the angle. In getting from the direction of one line segment to the direction of the other, the greater the turning that has to take place, the greater the angle will be. The size of an angle is determined with respect to an entire revolution. So the size of an angle is determined with respect to an entire revolution, and an entire revolution is obtained if the turning continues until we are back where we started from. So that's an entire revolution, going all the way around. So the turning takes place and we go all the way around. And that is called, what is that called, Jerry? One revolution. Alright. So that's one revolution. And notice that when we get to the end of that revolution, we do not put the vertical line onto the other. We put it close beside. As a matter of fact, it should go onto the other line. But if we put it onto the other line, it will appear as if a single line is there. So we actually just cause the line to be close to the other one. The line should actually be at the same location, but I am separating them in order that they do not look like one single line. As a matter of fact, this line should actually be on top of this one, but if we do that, it will not look like a revolution. It will just look like just a stick that is standing right there, and we are putting a curved line around one of the tips. But by so doing, we are just demonstrating that a second line should really be present. Your angle is a fraction of that 360 degrees. So any angle that you are representing has to be a fraction of that 360 degrees. If your angle is a quarter of that revolution, then it is 360 divided by 4, which gives 90 degrees. And you know that 90 degrees is the angle represented as one right angle. And it is also the angle represented by perpendicular lines. So perpendicular lines are at right angles to each other, and the angle is 90 degrees, and it is also a quarter of a revolution. 1/3 of a revolution is 360 divided by 3, which is equal to 120 degrees. Or we may have even 3/8 of a revolution, which will be 360 multiplied by 3/8, which will give 135 degrees. So any angle that you have will be a fraction of that entire revolution, and the entire revolution is 360 degrees. On the next slide, we will take a look at some angles and the approximate turn that they represent, or the approximate turn that is responsible for each of them. The approximate angle will be organized in order that candidates will have an idea of the sizes of some of the more popular angles. So this angle cycle is our new angle cycle, and it is more detailed. As a matter of fact, what we will call digit is a word that we may use, or we may use, or say each one of these. As a matter of fact, we have more of them, and we have them occurring in a smaller space. So we are going to take a look at some of the more popular angles. As a matter of fact, the angles will not be exact because they are constructed on a computer screen. So first we have our 30 degrees, another 30, 60, and another 30 will take us to 90. So each one of these is representing approximately 30 degrees, but not necessarily exactly 30 degrees. Approximately 30 degrees. The first indicated angles go up by 30 each time in order to give an indication of what a 30 degrees angle looks like. The ones that we have there are the 45 degrees angles. 90 plus 45, 135. 135 plus 45 will give us 180 degrees. Next, we have a view of the approximate size of a 45 degrees angle. Between 90 degrees and 180 degrees, we have two angles of 45 degrees each. What will we have next? After the 30 degrees, the 45 degrees, what angle do we have, Jerry? 60 degrees angle. And we will have three of them. So 180 plus 60 is 240. 240 plus 60, 300. And 300 plus 60 will give us 360 degrees. So there we have some of the more popular angles. 30 degrees, 45 degrees, and what else? 60 degrees. As a matter of fact, if you look right here, you will see your right angle, which is 90 degrees, 330 degrees, and the 90 degrees is here again. Of course, you have the angle on a straight line. The angle on a straight line is actually 180 degrees. So between 180 and 360 degrees, we have three angles of 60 degrees each. Notice that I kept emphasizing that the angles are approximate. If you put an instrument on the screen, you might not get the exact angle for a number of reasons. For example, the dimension of the screen. If we construct the angles on a particular screen of a particular dimension, if the screen is not proportionate to that screen, then the angles will be different. If the screen is of the kind of a wide screen, then it is going to be different from if it were constructed on a normal, approximately square screen, although we know it's not exactly square. But the dimensions and the shape of the screen is a contributing factor to what the angles will actually be. So you should not measure those angles on the screen, because you will quite likely not get the same angle that we have represented there. Mark and John are told to draw polygons. Which of these shapes drawn is not a polygon? Which one is not a polygon?
Option B.
And Jerry saying is option B. Why is it that this is not a polygon, Jerry?
Because it is round.
Because the lines are round. Actually, the lines are curved lines. And a polygon should have only straight lines. So Mark and John were told to draw polygons. Which of these shapes drawn is not a polygon? Option B. A polygon is a two-dimensional shape that is made up of only straight line segment. Only if the lines are straight, then we have a polygon. In order to identify the one that is not a polygon, we have to identify the one with lines that are not all straight. The examiners expect us to be able to look and identify that with surety. Option B does not have all straight lines. It represents our answer, but we will demonstrate that it is correct. So option B is our answer because it does not have all straight lines. So how will we demonstrate that some of the lines are not straight? Use straight lines to show that there are lines that are not straight in option B. So we will use straight lines. So we have those straight lines going up. Right. And notice that the two line segments here and here do not match with the straight lines. Because they do not match with the straight lines or the straight line segments, then we are sure that those lines or those line segments are not straight. Hence, option B is not a polygon, and it is the answer that we are looking for. There are portions that do not match with the straight line. So we have portions that do not match with the straight lines. And as a result, option B is not a polygon. It does not have all straight lines. Which of these diagrams shows a mirror line? Which one shows a mirror line? Students are expected to look at a diagram and tell if it contains an object and its image reflected in a given mirror line. Students are expected to look at a diagram and tell if it contains an object and its image reflected in a given mirror line. Your question is, which of the diagrams shows a reflection with the dotted line representing the mirror line? Which one shows a mirror line? That means, which of the diagrams shows a reflection with the dotted line representing the mirror line? At sight, the correct answer is option B. That is our correct answer. However, you will say that Richard James Mathematics Resources did not explain why. And we have gone through lateral inversion, reflecting. We have gone through symmetry, lines of symmetry, and how an object and its image are related relative to a mirror line, and what happens in a line of symmetry. We have done that on previous occasions, but we will continue. One of the theories that we may use is based on reflecting the object in the mirror line point by point. So if we look at the points or corresponding points of the object and its image, then we are sure to discover why the others are incorrect. Take a point on the object and the corresponding one on the image. A line joining a point to its image is perpendicular to the mirror line. A line joining a point to its image is perpendicular to the mirror line. So there we have option A enlarged. Let us mark a point on the object and a corresponding point on the image. Any of the diagram may be the object or the image. So put a point right there. That is A, point A. If we need to locate the other one, how do we do it? Be mindful that for a reflection, the image has to be laterally inverted or flipped over in the mirror line. laterally inverted or flipped over in the mirror line. So if you have your book, the center of your book is the mirror line, and the flipping over is as if you are turning over your page. And that is the effect that a mirror line will have on an object. Be mindful that for a reflection, the image has to be laterally inverted or flipped over in the mirror line. If the point is on the portion of the object that is further away from the mirror line, then its image must also be on the portion of the image further away from the mirror line. So we need to say A, and if we are proposing an image for A, it has to be away on the other side, because this is away from the mirror line, then, which is mirror line, then the proposed image has to be away from the mirror line. If it is approaching the mirror line, then the proposed image must be approaching the mirror line from the other side. Use a line to join the point A to its image, A prime. Is that line perpendicular to the mirror line, Jerry?
No.
Perpendicular means what angle?
90 degrees.
Okay, 90 degrees. That is by no means 90 degrees. So there you have your angle. Is that line perpendicular to the mirror line? Jerry said no. Does it form a right angle? A 90 degrees angle? No, it does not. It therefore means that this line that we have here is not a mirror line. Additionally, if we have to go through hell and high water just to find a point and another point that may be its image, then it means that it is not a reflection, and it means that the line is not a mirror line. As long as it is a mirror line, then the image or the image of a selected point should be easily identified. So there is your angle. We have the angle right there. It does not represent 90 degrees. Therefore, it is not perpendicular. That line is not perpendicular to the mirror line, and not mirror line to the dotted line, because the line is not a mirror line. We cannot call it a mirror line, and it is not a mirror line. So it is not perpendicular to the dotted line. So the dotted line is not a mirror line. The angle is definitely not a right angle. It means that the line that we have imagined to be a mirror line is actually not a mirror line, because the line joining a point to its image has to be perpendicular for it to be a mirror line. Let us take a look at maybe one of the other options. Understanding the relationship between an object and its image in a mirror line, we know that this represents the correct option. But we will flip one side of it around in the mirror line and show that the other side will be its image. So take a look at that. Flip it over there and flip it back over there. Flip it over there and flip it back over there. What do you notice? That when you flip it there and flip it there, that the formation that you have there is exactly the one that we have in the option. Therefore, this represents a mirror line. What do we know about a mirror line? that if you cause this to be the center and you flip this over, then what you have on the other side will be what we call a lateral inversion of this one. So if you flip it over, it will exactly be on top of it. So it will fall exactly on the other object. If we cause the mirror line to be the center, like for example, the center of a book, and you have a diagram on one side of the book, on one page of the book. When you flip it over, if it falls exactly on another diagram, then that represents a reflection in a mirror line, and that mirror line would be at the center of the book, and we will call that a lateral inversion. It goes over there and is formed right there and over there. So we are sure that that one is correct. Now that it passed the test for a lateral inversion, let us label a point on its image. In a mirror line, it does not matter which one we choose as object and image, as the two objects will be mirror images of each other. So if we call one object and the other image, or we exchange places, it does not matter, because it will still be a mirror image of the other or a lateral inversion of the other. So we have the point A and its image A prime. Let us draw a line from A to A prime. Is that line perpendicular to the mirror line, Jerry?
Yes.
Right, it is perpendicular to the mirror line. Therefore, this line is actually a mirror line. The line joining the point to its image is perpendicular to the mirror line. Because the line joining the point to its image is perpendicular to the mirror line, we are sure that this dotted line is correctly called a mirror line. Do not forget one test of the mirror line, or one requirement of a reflection in a mirror line, is that a line joining a point to its image is perpendicular to the mirror line. So there we have the demonstration of the fact that the angle is actually 90 degrees, or that the two lines are perpendicular. The dotted line that we are investigating has been proven to be a mirror line, and option B is correct. Why is it a mirror line? Because a line joining a point to its image is perpendicular to that line. What about that one? In this particular case, the mirror line passes through both objects. We cannot even reasonably choose a point and its image. So in this particular case, the proposed mirror line, the dotted line, passes through both objects. We cannot even reasonably choose a point and its image. If we flip one object with the mirror line being the center, the image formed will overlap with the original object. Why? Because the mirror line passes through it. If it were a mirror line. This is always the case when we reflect an object in a mirror line that passes through it. So if we have a mirror line and an object passes through the mirror line, then when we reflect that object in the mirror line, the object and the image will overlap each other. Since there is no overlapping and the mirror line passes through the objects, then we are sure that the line that we have there does not represent a mirror line. So let us read it. It should have been read this way. Since there is no overlapping and the proposed mirror line, or the dotted line, passes through the objects, then we are sure that the line that we have there does not represent a mirror line. How do we know that it does not represent a mirror line? Because if it were a mirror line, when the mirror line passes through an object and it is reflected in the mirror line, the object and its image usually overlaps each other. Usually overlap each other. So we are sure that because there is no overlapping and the line passes through the object, then we are sure that there is no mirror line there. If one of the objects were to be a lateral inversion mirror image of the other, where would the mirror line be? You have to show me, Jerry, on the diagram. If one of these were to be a mirror image of the other, where would you put the mirror line? And he's saying that he would put it in the middle. Show me, draw it on the screen, how you put it in the middle. So, right, correct. So Jerry is showing us that he would put it in the middle, going down, like that. So Jerry is well aware of what a reflection would be. What about that one? Let us mark a point on the object and the corresponding point on the image. That is your A, and your A prime is all the way over there. Be mindful that for a reflection, the image has to be laterally inverted or flipped over in the mirror line. If the point is on the portion of the object that is further away from the mirror line, then its image must also be on the portion of the object or the image that is further away from the mirror line. Also, nearer will correspond with nearer. So if we have this point, like we have this point right here, and let's say this is a mirror line, the image of this point could not possibly be here, because if this is to be reflected in the mirror line, then its image will be, since it's a point further away, then the image will be a point further away. Use a line to join the point A to its image A prime. What do we notice? The line joining the point to its image is not perpendicular to our proposed mirror line. It is not actually a mirror line. So that's not perpendicular. So this dotted line is not a mirror line. If n plus 4 is equal to 12, what is n? And Jerry is saying that it is 8. Correct. What we have there is an equation that we need to solve for n. We will first take a common sense approach in solving it. When we add two numbers, the result must be larger than the two of them. 12 must be larger than n and 4. Because when we add them, the result must be larger than the two numbers that we have added. So 12, whatever n is, 12 must be larger than n. Since 12 is the largest, whatever we do in finding n, n must be smaller than 12. By common sense, subtract 4 from 12. N is equal to 12 minus 4. What is 12 minus 4? We have to quickly put those up, because we have all 12 of them, and you do not have to count them, because we label them, each of them, with its number. So we will see that we have a total of 12 of them. And what are we doing there? We are removing or subtracting 4 of them. So how many are left? 8. The correct answer is option C. I hope that we shade option C. Correct. Subtracting is not the only way to get a smaller number, but at this stage we are only working with natural numbers, and we will not choose divisions as the opposite of addition. So because division is not the opposite of addition, the opposite of addition is what, Jerry? What is the opposite of addition?
Subtraction.
Right, subtraction. So we need to do the opposite of addition in arriving at our answer. We have 12 subtract 4, and the result is 8. In the equation, the unknown is on the left hand side, accompanied by a positive 4 or plus 4. So what we have here is an equation. We use two things to identify that expression as an equation. One, this equal sign. Equation, equal. So this equal sign. And two, the fact that we need to find the value of an unknown, which is n. So in that equation, n is accompanied by positive or plus 4 on that left hand side. In order to solve the equation, we need to just have n alone on that left hand side. So we have to take the necessary steps in order that when we are through, n will be the only thing on that left hand side, and not only that, but the steps that we take are actually legitimate. In solving the equation, the unknown is required to be the only thing on that left hand side. Just n alone should be on that left hand side. How do we remove 4 from the left hand side? 4 is added. So if it is added, we have to do the opposite of addition, which is
Minus.
alright. So if we minus 4 from that left hand side, then 4 minus 4 is equal to 0. So accompanying n on that left hand side, we will only have plus 0. And any number we add 0 to, we will get that same number. So if we minus 4 from that left hand side, then we will have 0, and 4 will be eliminated. So let us subtract 4 from that left hand side. Do not forget that we have an equation. Since it is an equation, it means that both sides are equal at all times. By subtracting 4 from one side, the equation is unbalanced. We have subtracted 4 from one side. It is unbalanced. We therefore have to subtract 4 from the other side to keep it balanced. So let us subtract what? 4 from the other side to keep it balanced. So if we have a plus 4, we will eliminate 4 by subtraction. And after subtracting 4 from that left hand side, the equation now becomes unbalanced. So we will have to subtract 4 from the other side. And by doing that, it means that we would have done the same thing on both sides. So we have to treat both sides equally. If we subtract 4 from one side, we have to subtract it from the other. By subtracting 4 from that left hand side, we have the 4 here minus 4, and the 4 will be eliminated. 4 minus 4 is equal to 0, and n plus 0 is equal to n. So we'll have just n on this left-hand side, and on the right-hand side, we have 12 minus 4. And 12 minus 4 is equal to
8.
The correct answer is therefore option
C.
The correct answer is therefore option C. Do you remember this step? Take a look at it. Here it is, where we subtract 4 from both sides. In a written examination, students do not lose marks for leaving out unnecessary steps, like the intermediate steps in solving an equation. So we have n plus 4 is equal to 12. The 4 which accompanies the unknown is related to it by addition. We need to eliminate it by doing the opposite, which is subtraction. We will do the same to the other side, as we have right here. As a result, 4 is eliminated from the left-hand side, but we still need to subtract it from the right-hand side. So what we have right here is that n plus 4 is equal to 12. So we need to subtract 4 in order to eliminate the 4 so that it leaves the unknown alone. So subtract 4 here, but we will have to subtract 4 from the other side also, that the equation may be balanced. Now what happens? The 4 is eliminated from that left-hand side, and we have 12 minus 4 on the right-hand side. But in an examination, that step is left out quite often, and it is not dangerous. It is not hurtful. It does not take away anything from your solution if that is done. Because of this, students are tempted to say that the 4 that we have that is added on the left-hand side is subtracted now from the right-hand side, which is not correct. How do we generally say it? Well, not Richard James, but some students and teachers say it. That what? When we have the 4 added on this side, it is subtracted from the other side, and that is not entirely correct. When the eliminated step is thought about, then we have the correct explanation. What is the correct thing to say? We say that we are subtracting 4 from both sides. As a result of that, 4 is eliminated from the left-hand side, but we still need to subtract 4 on the right-hand side, because what we do is we subtract 4 from the left, subtract 4 from the right. On the left-hand side, the 4 is eliminated, but we need to complete the subtraction process on the right-hand side. So the fact is, it was subtracted from both sides, which caused it to be eliminated from the left-hand side, but we need to complete the subtraction process on the right-hand side. Therefore, we did not subtract from one side, but from both sides. On one side, it was eliminated, and we need to complete the subtraction process on the other side.